Wow, I don't even recognize myself. The first thing I'd like to do is thank the VCs, the DVC, Procession, Executive Dean, for this occasion and this honor. Welcome the guests as well, and my wife, and good friends, John and Lee, who I've spent a lifetime with, and many others out there. What I'd first like to do, if you don't mind, is take my hat off. And as the VC was saying, it's pretty hot underneath these cloaks. So what I'd like to I've got a couple of preface notes first. The first one is traditionally, in an inaugural lecture, one celebrates a career, and I think the Executive Dean's just done a very fancy job of it. I'm sure some of that was embellished, but anyway. But what I want to do is I want to focus on what I'm doing at NMU. And most importantly is the vision I've got for this university and for the region. And hopefully I can energize you and I can excite you about what we're doing at NMU, because I honestly am very excited, and it's a great privilege to actually be part of this university. When I look and I speak to colleagues at UCT, they often, oh, well, you're at NMU, but we can grow. We've got a lot of room to grow, and when we do grow, we make a massive impact compared to UCT. So that's what I'm excited about. So this title begs an explanation. And I quickly ran it off when Renee wanted a title, and then I thought back to it, and I thought, this is a great title. Big thinking and big science. And the problem with us, we run around in our daily lives, and we very, very seldom ever think big. And it is an absolute privilege to think big. And it's usually in academic circles that you have the luxury of doing this. The second part is, can Africa grow intellectual research capacity and fix its developmental challenges? That's provocative. And I wanted it to be, because when people read that, I'm hoping that immediately an opinion comes into your head. I want you to sit up, stand up, and I want you to shout out and get energized from that. And that's the basis of this talk. And then the last little bit, not so little, ocean sciences and marine food security at NMU, a test case. What I'm going to tell you tonight is actually an experiment, and I honestly don't know how it's going to end. But let's have a look. So people often ask, what is ocean science and food security? This over here, this panel over here, can you hear me all right still? Can we have the lights dimmed a little bit, please? This panel over here, you can't see it all, and it's fairly detailed, but what it's saying, which many of you know, is that the ocean is an extremely complex environment. Unlike agriculture, if you think about maize, you've got soils, you've got moisture and everything. The ocean has got major physics, planetary physics, that's pushing and shoving water around. And in there, you've got a whole lot of fertilizer, you've got nutrients. And those nutrients have to be raised up into the photic zone, into the light levels, for plants to grow. And I often tell the kids, the phytoplankton is the grass, the zooplankton are the moo cows. And that then starts a whole chain of trophic levels of fish that eat other fish, and they get bigger and bigger, thanks, VC. And then you have an ecosystem with the big predators, the big fish at the top, and humans live at the top of that system. And over here, I've got an illustration of a prawn trawler, and I've got a picture over here of someone, a small child, who's busy grabbing fish. And that's the reality here. These people and these industries are dependent on the planetary physics, and I'm going to illustrate that tonight. Now, my wife actually just told me a lovely story this morning. Someone asked my daughter recently on the weekend, what does her dad do? And she said, oh, he's an oceanographer. And that person said, wow, it must be lovely going around the world taking pictures of the ocean. So there we go. That's another angle on the whole thing. So our job, my chair, is to use scientific methods to transform and to characterize these components and these relationships into scientific understanding. But one of the differences between ordinary oceanography and food security is we have to forecast. Now, a lot of times, oceanography doesn't do that step. We have to. And what we have to do is forecast, because we need to give governments and society answers about what's going to happen. And that's what food security is all about. So what I've done is instead of spending a lot of time about a lot of oceanography, a lot of detail, I'm going to pull the guts out of what I've just told you. And I'm going to talk about a humanitarian disaster that very few people actually know about on this planet, even governments. And then what I'm also going to do is I'm going to teach you 101 oceanography, a little bit of ocean physics. And then I'm going to go to the main challenge, which is going to be the thrust of the lecture. So the area I'm going to focus on is this over here. We call it the Western Indian Ocean. And the lecture is going to focus on how a problem, a humanitarian problem, is starting to evolve there. As I say, that not many people understand or know about. I'm then going to tell you that this problem, dealing with people, is part of a much bigger system, an Earth system, Earth science. We're talking about planetary science. And that's where my third component is going to come in. Big thinking, big science is required to solve this problem. And then lastly, the last part, I'm going to actually paint doom and gloom, that Africa can never, ever solve this challenge. But there's a way we can get around it, and that's what I'm doing at NMU, and that's the exciting part I want to tell you about. So let's just go back to what the VC was talking about, people. This is a little graph here. I'm sorry for those sitting right at the back there, but it goes back 160,000 years, and it tracks the population on the planet, the hominoids, and it trundles along until about the 1600s, and then I don't know what happened, whether they used Viagra or whether something went on, but we started flipping, multiplying like crazy. The power of exponentialism. And it just grew. And by 2005, as you probably all know, we had, well, that was 2005, we had 6.4 billion people. The projection is by 2050, we're going to have 9.1 billion people. Let's have a look where those people are distributed. Each dot is 1 million people. Look at India, Southeast Asia, Europe. We've got east coast of America, especially this over here, Mexico and everything. Let's go on Africa. You've got Central West Africa, but look at this down the east coast of Africa. 60 million people. So you'll notice that I often refer to food insecurity as opposed to food security. So this is an interesting little experiment. What you're seeing now is NASA's image, you've probably seen this, of the lights on the planet. And this has taken many, many loops of satellites going around. And those are the cities at night. Now let's just have a look at that. Look how they transpose onto the populations. India, Southeast Asia, even Australia in the middle of the outbacks has got electricity and lights. Europe, East Coast of America. And electricity or electrification is a really good indicator for two things, GDP and technology. This is now a graph showing how these areas have accelerated from 1990 in the production of electricity. There's Asia, Latin America, and Africa down here. We have a very low capacity, and that shows up so clearly in Africa. Very, very little electrification. It's not difficult to understand this, but if you look at this map here of rich and poor countries, with the light gray and the other color, darker gray, being the poorest countries in the world, you'll notice that they're sitting in the darkness. And if you have a look at GDPs, you'll see that America, Japan, and Europe have rocketed up. And we've got countries down over here. Particularly, you've got Asia, excluding Japan, and you've got here Africa, stubbornly resisting growth in GDP. Now, this is an important point. I want you to remember this, because when I get to the big science, we're going to start talking money. And it's not difficult to work out that if you start looking at maps of food insecurity, in other words, hungry people, it completely overlaps low GDP and low technologies. So as I said, what I want to do is focus now my lecture on this area here, the Western Indian Ocean, where 60 million people live directly dependent on the ocean. That is a village in Zanzibar. Fishers go out each day, they catch fish, and those people wait for. This is Zanzibar, 101. You've all been to Zanzibar, most of you have. It's 120 kilometers long, little island, perfect experimental island for this. you've got 101 fishing villages. The fishing, this is a typical craft that the guys use. A canoe with some outriggers. They go out and they use simple kit. Look at this, fishing line, old fishing lines and bits of hooks and stuff to go out and catch their fish. They've tried to, NGOs have tried to actually stabilize the communities on seaweed farming, sea cucumber, introducing a little bit of aquaculture. But at the end of the day, this little guy up here exemplifies what's going on. Their lives are going out, even at a young age. The only thing these guys learn is to go and fish. They are 100% dependent on these fish. This is Zanzibar. The boats have just come in, small pelagics. We've got the ichthyologists here. I can't remember, Warwick, if this is sardines or pilchards, but they're divided up into family groupings. That's the whole day. Let's look at this lady over here, walking down an aisle in Sainsbury's in London. She's been working all day. She has half an hour to quickly go and grab some food, and she's got a massive choice. Look at the contrast. This is the fishing village, Stone Town. The dhows come in. This is the fish, these little bits of fish over here that the people are living on. The big fish, all nice big grunts and stuff, they all go to the hotels because they're worth value. The population is left with the little fish, some of them so small they're that big, they have to dry, boil, do all kinds of things. So this now I've painted how you've got 60 million people dependent on that ocean. But what we've got here, this is ocean temperature, is that the ocean in the background, and this is Indian Ocean temperatures, the gray there is a steady increase, and I'm sure you all know this, that the oceans are warming. But the Western Indian Ocean, this little area over here, is warming faster than anywhere else in the world. It's warming, it's the fastest corner of water on the planet. If we have a look at this block over here, it's known as the Seychelles Chagos Thermocline Ridge. It's where winds suck up deep water with nutrients into this zone here, and it stimulates phytoplankton, the little plants. And we have a look at this graph here. I'm sorry, the back people might not be able to see this, but here the the red is the temperature, and you don't have to worry, that's over many years. And we can, this is measurements, we can track the temperature going up, but what's happening is the food, the amount of chlorophyll in the ocean is going down. What's happening is this is now a food web. You've got the phytoplankton, you've got the zooplankton, and then you've got the little fish, and you go up the trophic levels, and at the top you've got tuna and sharks, the big predators. What we're doing now is we are decreasing the amount of food in the absolute Achilles heel of this food web. And so what happens, if you have a look at, for instance, this is tuna, who operate and they move across the Indian Ocean. This blue is where they're caught. They come here to feed and to grow up, and they rely on that ecosystem. And this now is a plot over the last 50 or 60 years of tuna catches. We decimated, absolutely decimated the herds, the biomass. Oops. And now what we're trying to do is we're trying to recover this fishery. We've got little hope in trying to build this because, as I've just shown you, the food webs are beginning to collapse. But that's not the only story. You've all heard of El Nino. So the last El Nino, a year ago, was the strongest El Nino on human record. It's devastated just about 70% to 80% of the world's corals. Doesn't sound much, but in this ecosystem, these fish, they may not be big, but people are living on them, actually disappear because you are breaking down the coral, which is the fundamental component of the ecosystem. And these guys have nothing to eat. So what I'm showing you is this huge dependence with 60 million people who are undergoing these changes. They're also destroying the habitat using dynamite in some places. So you're blowing up the coral reefs and stuff. You've got an increasing population. You've got overexploitation, and all these forces are coming to bear on these ecosystems now. And we've got basically a humanitarian crisis that's slowly unfolding. But it's going at a very slow rate, and there's very little information. And so governments in the region are not even aware of this. That's one of my jobs I do, is I go around to try and educate people what's going on. And every now and again, you end up with a little thing in the newspaper. This is the Seychelles newspaper. No fish, no fishes. So, unrecognized. So that's the first part of my talk I wanted to introduce you to. The second part now is I want to tell you that what is happening cannot be studied just in the Western Indian Ocean. The Indian Ocean, or this section here, is part of the Indian Ocean. And the Indian Ocean is part of an Earth system. And that's what people do not fully understand. It's this coupling between water, land, and atmosphere, and the three come together. If we didn't have land, it would take you probably about 3 hours to learn oceanography. The winds would all go around the planet, if that was just a blue planet full of water. The winds would just go along in the zonal winds. You'd get the polar easterlies, you get the westerlies, you get the trades, and the water on the surface would be blown in that direction. Simple. But what happens is we've got continents on our planet. And what the continents do is they break those zonal regions up, and you end up with these gyres. Now, you won't be able to see this, but I'll describe it to you. So this is the wind now, and the wind goes around in the South and the North Pacific Ocean, the same in the Atlantic Ocean. The currents, I'll show you, are doing the same thing. But look at the Indian Ocean. You've got a massive chunk of land that's sitting in the northern part. It has no access to the North Pole. And it's got the Himalayas over here. So what actually happens, that land heats up and it cools down. Heats up on a seasonal basis. And that causes a pressure gradient between Asia and the Western Indian Ocean. And so you've all heard the monsoon winds. They are unique on the planet. These are the currents now. So here is our little blue globe, very simple currents. The currents, the wind follows the currents follow the wind. So in the Pacific Ocean, which is the prototype circulation, you'd find on Mars or anywhere else with a similar sort of continental configuration, you end up with these gyres, north and south of the equator. The Indian Ocean is completely unique. This over here illustrates that you have a completely different current system operating in the north and in the south. So what I'm doing here is I'm building up a bit of a picture of how unique this area is. And just to confuse the situation, you've all heard of El Nino, but you get another thing, a little El Nino called the Indian Ocean Dipole. And these warm bits of water sloshing around cause convection and further complicates it. So the message is here is that we're dealing with a very, very complicated feedback system between ocean, atmosphere, and land. That's the story. You don't have to take anything else away. So that's the northern, unique in the world. And those people are dependent on that system, that monsoonal system. Let's hop across the equator now and go to the southern Indian Ocean. Ordinarily, like in the Pacific, you end up with a current that's just beneath the equator called the South Equatorial Current. It goes across from one side of the ocean to the other, smacks into a continent, divides itself, and we call those boundary currents. Very powerful. The most powerful on the planet. In fact, if the Agulhas current stopped flowing, you'd have to adjust your watches because you'd end up with a change in the speed of the planet. Now, Indian Ocean, southern Indian Ocean, we've got this unique configuration of bathymetry and land. We've got this cirque over here, and we've got Madagascar. They aren't small. You will all know this cirque by the name of Mauritius and Seychelles. Mauritius is over there, and Seychelles is over there. But what you didn't realize is they're sitting on Table Mountain. This is the Mascarene Plateau. It's 4,000 meters high. I always tell students, when they're in Cape Town, you stand at Cape Town Station, look up at the cable car. That's 1,000 meters. Go up another 1,000 meters, and at the end of 4,000 meters, you're looking straight up in the sky. This is colossal. It's 3,500 kilometers long. It's a block of rock that sits in the ocean. What happens now, in this particular case, is the southeast equatorial current now strikes the Mascarene Plateau. You end up with a whole lot of water going through all these channels in it, deep channels, 1,000 meters deep, and you end up with a thing we call turbulence. When it reaches Madagascar, it splits, goes north and south, and because of positive vorticity and physics, it picks up big swirls of water. And so what happens is in the Mozambique Channel, you end up with these colossal 300-kilometer wide swirls of water, just busy going with super fast currents in them, 4 knots. And these things propagate because of planetary physics. And they want to go west, but they can't. So they start propagating down the western side of Mozambique. And for many years, We used to see in satellite imagery, now from satellites, the color, we can tell where the plants are and the phytoplankton, and you might be able to see these wisps of chlorophyll being taken off. And we never quite understood that. And then when we went and drilled it, we took ships, and for instance, we took a ship over here and we drilled it, we blow equipment and stuff like that, and we measured temperature. And what we found out is that over here, next to the shelf of Mozambique, because of these massive swirling mesoscale eddies, is the technical word, you end up with upwelling. Cold water means nutrients, and nutrients going up, and voila, you end up with food through plankton. So what I'm saying here is that, in fact, this area of the Mozambique Channel is a turbulent-driven ecosystem. Now, the north was wind. This is turbulence. This is swirls of water going around, and it's still producing upwelling and stuff. If you have a look at what happens to these, now this picture here, it's amazing in oceanography. We use these satellites and all these measurements so flippantly, and you look at something and you automatically think people understand it. Now what I'm doing is I'm looking at the height of the ocean. And from the height of the ocean, which is only a few centimeters, we can calculate currents. And so this now is basically currents, but you can see these mesoscale eddies propagating down Mozambique Channel, coming into the Agulhas current, and they propagate down the Agulhas current. By the way, the Agulhas current is the strongest current on the planet. By the time it gets to Port Elizabeth, these eddies end up causing meanders going offshore in the Agulhas current. And these meanders are capable of pulling shelf water near Algoa Bay. We've seen it being pulled off into these things, and then it's lost. The thing is here, is right here, as you all know, we've got a fleet operating the squid fishery. These guys here are looking for this on the seabed. Here you've got a whole lot of squid, male and female squid, coming down, doing the nuptial dance, coming down and laying eggs. Those eggs take 3 weeks to hatch, and out pops a little critter, 2 millimeters long, a little paralarvae, and he can't swim. He's advected by wherever the water's going. And so what happens is that, I should say what did happen, so I haven't given you the story about these little guys floating around the water, is the squid fishery, which has gone through a couple of ups and downs, 2013-14 witnessed the worst crash it had ever seen. We had a huge problem. Boats are bought by individuals. They're not subsidized by government or any other big corporations. And so people would go to FNB and borrow 20 million rand to buy a boat. You have to pay back several $100,000 a year on that boat. And of course, no fish, you can't pay the boat back. We also had huge social unrest with the fishers. 2,400 fishermen, but about 30,000 dependents. What we think, and then what happened just after that, the fishery recovered. So the big burning question here is what happened and will it happen again? And so one of the hypotheses is that those little critters, those little larvae were pulled off so that into the unknown. The message here I'm trying to give you is that ocean physics that started near Australia had an impact on people of South Africa and the Eastern Cape. So the burning question is it going to happen again? Where is this ocean system going? We need to somehow predict it. If you take traditional measurements, whether they're through satellites or whether they're through putting a thermometer in the ocean, we can get 30 years, 40 years. In this case, we've got nearly 100 years of data. But what's it going to do in the future? Do we take a ruler and we just regress through here and assume it's going to go up like that? Or do you think it's going to go down and go up? We've got no way of predicting what's going to happen in this very complicated system. So that now is the second part of my lecture. The third part is the part I want to now talk about, the big science and the big thinking. So this here is an animation of one of the biggest computer models of the oceans and the atmosphere in the world, called NEMO. And what you're seeing there is currents. This is all currents. People ask, how on earth do you make a computer model of the Earth's oceans and climate? And this is how we do it. We build it up with what we call a mesh. We divide up the atmosphere and the oceans into this mesh system that has levels, depending on the model, can go 20 to 30 to 50 levels. and the same in the atmosphere, and the same in the ocean. And what we're trying to do is we're trying to recreate all these processes that we find on Earth. We have to have some areas we've got to zoom in, so the mesh needs to be much tighter. It needs to go down into almost a kilometer or so. In each and every single box, of which there are hundreds and hundreds of thousands, we have 27 equations, accounting for momentum, energy, mass, water in the case of atmosphere, and equation of state. So to predict what's happening in that box, we need 27 equations. What we're trying to do now is we're trying to mimic not just big events and how the oceans work on a global scale, but we're trying to catch these things, hurricanes, and we want to go finer into tornadoes if we're going to be accurate. So what we're doing is we're bringing in a field called fluid dynamics, computational fluid dynamics. We've got the meshes and we've got the equations, and we're trying to mimic what's going on over here. This now is an output from a global ocean model. Every single little dot from the back there, little vector, is in fact one of those outputs from those 27 equations. So you can imagine how many computations the model has to make to try and figure out what's going on in each block. How do we do it? We need the biggest computers that humankind has ever made. This one is the NASA computer Discover. And this one here is the recent one just been put into Australia. Built in 2012 and updated in November 2016. These machines here are the power of 15,000 laptops or PCs. They can do 57 parallel calculations at once. So a problem is divided up into 57,000 pieces, if you want to think it that way. And everything's done at the same time and brought together. These things are huge. They're expensive. And to give an example, this particular beast of a machine cost 500 million rand. And to operate it costs 120 million rand per year. And that's not even including the updates. So you can imagine trying to do those calculations and the computational power that these ocean climate forecasting models is. So let's just stop now. Let's dwell on what I've just told you. I've been building up a picture about people who are dependent on the ocean, and we need to work out what's going to happen to those people. And we can't use a little ruler any longer. We've got to use one of these types of Earth climate model systems. And this is the toy we need. Of course, these are national facilities, like anything. This particular one in Australia, it lives in Melbourne, but it's available to certain universities. And by the way, this lives at a university. So there's the take-home message is that's a big toy we need. The problem is with a model, an ocean model. It's got a whole lot of mathematics in it, and we start the thing running. And the maths all is correct. It trundles along and it pumps all kinds of little numbers out, and you've got a current going there and a temperature and everything. The question is it right? Is this right? I can't just go along to the Minister of Mozambique Fisheries and say, listen, your fishery is going to crash. He'll say, but what basis have you got? So we have to ground truth these models. We've got to feed them real data. And the only way we can really do that, driving a ship around only does a little bit. We need to actually use constellations of satellites. So satellites are able to measure salinity, temperature, the height of the ocean. They're able to measure gravity, for instance, which we use in oceanography. So we can measure a whole suite of things from these satellites. This is now Jason 1 and Jason 2, trundling along. They work, these two in a pair. Also, cost a lot of money. They're going along now, and can you believe it? They're making 20 observations per second. They have a swath on the ground of about 10 kilometers, and they can measure the surface of the ocean within 2 centimeters. That's incredible, from 800 kilometers. And they're covering the globe with tracks, ground tracks that are 300 kilometers-ish apart. Imagine the data that is coming out into these ground stations. This little movie I'm going to show you is, we call this altimetry, the height of the ocean, being measured by generations of satellites. This now was 1978, our very first ones going up. And look at these red dots here. This is the next generation, 1986 to 1990. Look at the resolution we're getting. Our toys are becoming refined. We're beginning to get better observations. Those are those red dots. We're starting to see a whole lot of differentiation. Look at this. This is now our present. Look how we're getting a finer and finer resolution and understanding the ocean. The first stuff we've been collecting is rubbish. Well, not rubbish, but it's fairly inaccurate. And the new generation, which will pop along in a moment, this is now, the satellites are going up in a few years' time. 2020, the new generation that are almost ready to be launched. Look at this. Incredible detail. That is a detail we need for these models, but it comes at a cost. We need another supercomputer to be able to handle this lot. This now is an interesting map. I got it off a chap who works for Times Media, who most universities hate. This is the top 1,000 universities in the world, and unfortunately NMU doesn't sit up, it doesn't have a dot. They've plotted it, believe it or not, on an atlas of the world. So here's Africa over here, this is Europe, this is North America, this is South America, Australia over here. And what they've done is they've plotted it in relation to the GDP of the country. So what it's saying to you here is that the top 1,000 universities on this planet all are up in the Northern Hemisphere, with the exception of Australia. Africa has got 2 universities that show, WITS and UCT. South America hasn't got one single university in those top 1,000. You can plot this the other way around. This is the population versus the universities. Look at the size of Africa and the size of South America, and no universities. Or top universities, I should say. For those of you who couldn't get your head around that, this is a simpler map. This shows you the universities, the number of universities throughout the world, and you can see again, Africa over here has got very few world-renowned, highly capacitated universities. And let's just drop in the food security map again. So what I'm telling you here is I'm talking about, to solve this problem we have in the Western Indian Ocean, we need some big toys. And the take-home message is, guys, we can't afford this science. It's way, way too much. I've just tried to get a PA out of Andrew Leach. I don't know if Peter's like this, but by God, can he duck and dive? I just want a PA. I don't want a supercomputer. But it illustrates where we are, is that money is tight. We've got fee issues. How am I going to get R500 million to build a computer at the Ocean Sciences campus? Andrew, we need to think about this over dinner. Okay? Let's just embellish this story a little bit further. This is what I call the Indian Ocean research capacity gradient. If we go to the eastern side, this institution I was at in January in Perth. Huge, R500 million to build that. 130 staff, 82 PhDs. If we go to the center of the humanitarian problem I'm telling you, which is Zanzibar, here is IMS, the Institute for Marine Sciences, part of the University of Dar es Salaam. I was there the day before yesterday and the day before that, Saturday and Sunday, working with these guys. A staff, 20 staff, who are probably earning quite close to about 400 rand a month of PhDs and professors, maybe 1,000, and they've got 15 PhDs. If you look at their research capacity, their research vehicles, this is the new Investigator, launched in January, built by the Australians. And this is Tafiri. This is their research vessel, a ski boat. And this is the Kenyan vessel over here that we're struggling to put petrol in. Can you see this massive contrast in capability? So the bottom line, as I say, is that it looks like Africa can't afford to play this game. We're going to have to ask people to solve our problems. And this little illustration is the last one I've got, embellishing capacity. I had 6 PhD students from Mozambique when I was working in Cape Town at UCT. 6. They did fantastic PhDs. Some of the best PhDs I could have ever dreamed for. 5 went back to Mozambique. None of them are publishing their PhDs. And only 1 managed to get a job. The one who's got a job has 2 other jobs because he can't earn enough money to live on it. So he can't do any science. These are the problems that we are dealing with. The other guy, Isifu, who was with me, in fact, on Sunday, stayed on in Cape Town, managed to get a job at CPUT, Cape Peninsula University of Technology, and he's now publishing like crazy. So there's a story here. Africa is littered, absolutely littered, with these capacity building projects, and I absolutely hate them. Because what happens is these rich nations, capacitated nations, they go in, they have a workshop, they take a student, they pull him into Sweden, they give him a PhD, and they send him back to an institution that's got a couple of buckies and a ski boat. And they're asking the guy to do world-class science. It doesn't work. So this is the last part of my talk, and this is why I'm standing here, and this is why I'm at NMU. And this is why I was funded by the Newton Fund and the NRF and the British Council and so. So I was very fortunate to get a chair. When I was applying for the chair and we were putting it together, they said, Mike, I know you're an oceanographer, but you've got to choose food security or water. Can you make this work? I said, jeepers. Of course we can get it to work. It's a natural application of oceanography. So they're thinking there's no rocket science. It's really simple. Let's just build a pipe into the rich north and just pipe down that capacity. It's not difficult. Okay, and we need to do it quite fast because actually there's a bit of urgency we've got here. In a more formal way, this is what I'm doing. I'm building what I call an innovation bridge between the rich north and us down here. Now, we're not that poor down in South Africa, but we do need help. This is where my office is, and this is where I've tucked in. I've managed to sneak into a British establishment. And because half my salary is paid in British pounds, I am a British government employee. And that sinks me right in the heart of their funding system. The other half of me is at NMU, and that sinks me in the middle of you guys, on the east coast of South Africa, which is the most perfect place to do oceanography. But first, we've got to reach out. We've got to reach out into the region as well. But we can't do it all at NMU. And that's why I'm so chuffed Peter Clayton's here, the DVC of Rhodes. I'm so chuffed that Warwick's here and David Vousner here. Because this is what I'm trying to do. I'm trying to build a center of excellence because we can't do it all at NMU. We need this scale of problem. You need multiple institutions. And so this is one of the things we've got to do. We're building a partnership. We are going to focus on the ecosystem side, is what we're good at, the modeling and all that stuff. And they are going to bring in the fishery side of things and the socioeconomics and the ocean governance. So what I'm doing now, I was there on the weekend, I'm building the regional hub here. I'm trying to lock in to these facilities in the region where the problem is actually happening. Cape Town, Port Elizabeth is a wonderful landing site for all that technology because it needs a lot of support. We can't do that at IMS, as I showed. I want to give you another little story here. This here is the new institute at Zanzibar for IMS. It was built 4 years ago by the Chinese. I visited it about 10 times. There's nothing in there. There's no road going there, there's no water, and there's no electricity. But the Chinese built it. But they built it for fishing permits. So they got their fishing permits, and they've pulled out. Professor Johanna Shigodi, doesn't have the money to buy the furniture, to put books in, and literally to buy laptops. So I don't know, I might, Andrew, move off in 5 years' time when I built this to try and help these guys, because it's all part of this network. It's an interesting story. So this is what we're building. We're building what I call is an innovation bridge and regional hub. And we are pulling all the resources in the region together to operate together. So the VC mentioned the new Ocean Science Campus. And I know I've got a couple of daggers in my back from peers and stuff because there's huge jealousies. And there should be, because I think it is world class. It is a fantastic facility. It's only, as a VC was saying, it's only phase 1. But here we've got 2 wings. This here is the ocean physics over here. That's driving the physical side of the ecosystems. Just across through the House of Commons is the biology. Look at the lab facilities. These are flipping world class. We've got tanks where we can do growth experiments. We can start growing plankton and start poisoning with various things. Throw more oxygen at them, less oxygen, CO2. We can do all kinds of experiments. And this is the part that I love, is the ocean physics. I'm so proud of that place. When you walk in here, the floors are squeaky, shiny clean. We spent so much time looking for a clean environment because gliders, millions and millions of rands worth of gliders are coming in to basically be prepared for these experiments we're going to be doing. These are the toys we're piping in. This allows me access to Hector. Hector is UK's computer, and it's top secret. No one knows where Hector is. There is a service, typical English. Everything's privatized. So if I want to use her, I have to basically borrow probably in the region of about 120 million rand to do a run on her. I don't know where she lives, but they'll help me do the experiment. So I now get access to Hector. In fact, we at NMMU are going to have an ocean modeler starting next year who will be working with Hector. So these are the toys. I get access to all of this, and I get access to that. So the pipeline is working fantastically well. I've now just recently got the ships sorted out. We've signed a contract with DAF, Department of Agriculture, Forest and Fisheries, for a lovely little ship. You're going to see her floating around here. We've got the Kenya vessel that I'm paying £35,000 for, and we're busy gearing up for her. And then I've got the French vessel. And one part I'm not telling you is that there's also an innovation bridge that I've built with the French as well. Sorry, British High Commissioner, but we need everybody, okay, on board. So I've got a French vessel on board. So, hey, man, this picture's coming together really nicely. The other part, as I said, that's all the heavy physics stuff and everything. The other part is we need to have roads on board. And Warwick Sauer, Professor Warwick Sauer, is head of department, and Warwick and I have spoken for decades about dreams like this. Rhodes comes with decades of experience in Africa. They've pushed probably, Warwick, 1,000 students, postgrads through, maybe more, and they've got all of this network into Africa, and they've got quite a phenomenal team. So this is now what Peter Clayton, the VC of NMU, the DVC of MU, we're going to sit down and we're going to actually start talking about this relationship. There's one thing about this. It's all very well doing all the science, but we've got to get it into those international structures, into those governments of Mozambique. Okay, and that's a subject called ocean governance. And I must say, I'm brushing through all this very quickly, but each one of these things I'm talking about is hugely complicated. I mentioned satellite altimetry. Satellite altimetry would require PhD experts in this room to basically analyze a couple of days of data. When I talk about ocean governance, it's a new topic. It's at the cutting edge of ocean science. And you know what? We don't have a single completely employed professor of ocean science in South Africa, if not in the region. So coming back to this network, I've painted the story of the network. We need a research plan, and that's one of the first things I did in my job, is I wrote the research plan, and I broke this area up into 9 different ecosystems so that we can manage the problem. You can't study the whole thing at once. And we're going to slowly bite-size our way through this whole thing. And of course, remember, I told you that each one of those ecosystems is dependent on the Earth system. And that's where the big thinking comes in. Big thinking, big science, big toys. This now is the experiment we're going to basically do in February 2019, straight off NMU of Port Elizabeth. This is the most complex, expensive experiment ever been done, arguably in southern oceans, in southern hemisphere. We are throwing an arsenal of equipment. The big toys are coming down. We've got 3 ships, 2 ships and 1 boat. Ryan, sorry. She is a ship, isn't she? We've got 3 ships, so we go from the very big to very small. And we've got a sleuth of toys that we're throwing in to look at this problem with the chocker fishery and trying to understand and model and where it's going to go. So, summarizing what I'm showing is that we've created the most phenomenal network to grow PhD students. We've got excellent infrastructure. We've got a vibrant network, and vibrant, I mean people all the time being engaged, teams in Kenya being part of a massive team. Those PhD students in Mozambique would be brought into this system. They aren't going to come and spend time here. They're going to spend time in Southampton. They'll go back to their institutions, but we never leave them by themselves. They're always fully supported. We've got top-end skills, top-end that you can get. We've got critical mass. People in South Africa are asking me, Mike, surely, or overseas, they say, Mike, surely South Africa has scientific capability to solve this problem. We haven't. We've got actually Eckhart Schumann. How many physical oceanographers do we have in this country? 12. That's it. Eckhart's retired and we still pull him in. There's hardly any of us. So we're building critical mass very quickly, instantly almost. We've got world-class supervision for our students. I am the world's worst supervisor. If you manage to get a master's or a PhD from me, it's a miracle. And the reason being is because I'm traveling all the time. I'm the guy talking to the governments, trying to get the science down, trying to buy the toys, bringing this machine together. The students struggle to get hold of me. I need to have world-class supervisors, and I've got them. University of Southampton, NOC. So immediately, the students that we have next year, and already, are being supervised by some of the top scientists in the world. And then, of course, there's the funding, which I've already told you about. Okay, I was able to get big money through this bridge. And then, of course, the final thing is scientific leadership. You know, it's quite interesting. Warwick and I were talking about this over several beers on Sunday night. It's interesting. You know, we all started off. I started off my research career through Warwick, actually. He told me to go to a little place down the road here, St. Francis Bay, and to put down a current meter mooring, because that's where the chock are having problems. We both dived down. I got down. It was pitch black. Couldn't see a thing. We got to the top, and Warwick says, "Hey, it's lacquer, hey?" So that's where I started. And I thought that that little current ocean that little circulation in Crom Bay was everything. I was battling to get my head around it. And then it grew. Then I needed to know another problem. And then it grew, and it grew. And then I started growing into South African science. I wanted to know how the Agulhas Current was affecting that little bay. And now, as the executive dean was reading out, now I'm an expert on an entire half an ocean, if not an ocean now, because I know what's going on the eastern side. That's incredible. And this is the thing, is you can't just get there. It takes a lifetime of research to gather that knowledge. And people often say to me, they say, the students will come to me and say, and I'll look at a graph and I say, that's wrong. And they say, but how do you know it's wrong? Because it doesn't fit the pattern. I know what the pattern's looking like. And the best PhD student I ever had was a Brazilian. And he wrote his entire chapter, one of his chapters in his PhD, with no data. And he gave it to me. And there were graphs and everything. I said, Rodrigo, how on earth did you get this? He said, Mike, because I know what I want. Rodrigo turned out to be a fantastic scientist because he knows what he's looking for. He knows what the result should be and what the data should look like. So in a nutshell, I've created a vision for all of us. Now let's have a look how far I've managed to progress along here. This is a little time map. And I don't know if you can see John and those at the back there, but we started in the beginning of 2016 when I took the chair. The first thing I did was the British Council Newton Fund, NRF, gave me the job. Fantastic. Then I was able to start concentrating on a full-time basis on developing that research plan that I showed you. I started looking for money. Already last year, in about July, we were starting to design what we needed. And this is great, because I know what is needed for this big machine. And so I was able to engage right from the foundations of what we've got. The toilet needs to be there. The coffee machine needs to be there, and so on. So, and then with just about no money, we managed to do our first cruise off Madagascar. So the very first NMU students already went off, and we executed that cruise over there. Come into 2017, I couldn't believe it. April, we got that 160 million rand GCRF grant. That was the biggest boost we could have ever had, £8 million. At the same time, or a little bit further on, the Ocean Science Complex was finished. Then, and I've put this in, Ryan, being a little bit presumptuous, but maybe we might get our second lot of funding, which is through ASEP. How's that? Maybe not, but we're hopeful. 2.5 million rand is not a lot of money when I start mentioning figures like 160 million. But in South Africa, it's a lot of money. 2.5 million rand for us is a lot of money, so it's greatly appreciated. What comes with that 2.5 million rand, if I can get my little machine to work, is ASAP has got a whole slew of toys of support for us. So we build more support into the structure already I'm talking about. But the interesting thing here is we're building toys that can cope with smaller processes. So now we're spanning from supercomputers, satellites. We're able to go down to a little boat, and we can go and take some measurements directly off here that are just as important in understanding the whole process. So just recently, so I should say over here, so we've got some students, and they will be graduating. Our first intake will happen in February. Officially will be in February. Adverts are going out next week. And then we'll start our production of PhDs and MScs. We've got cruises and fieldwork that's happening in 2019. We've got the big toys coming in, and we've already got our first issue on the Madagascar ridge coming out next year. So we're actually doing really well. We've got these special issues on the Kenya area, Tanzania area, being following in a few years' time. So in a nutshell, what I'm telling you is that in 1.5, 2 years, we've really done quite well, very well. And this is where I was on the weekend, is building the regional hub, getting the guys to join this hub system. So the machine is nearly there. I've got a few things to do still. The VC and I need to go and start stomping and banging down the doors to find 50, it's a little bit of money. I need 50 million rand more to buy some toys. What the Brits are lending us the toys. We don't own them, they go back to the UK all the time. We need the toys to stay here so we can grow new students, new PhD students on these toys. We can develop. I need 50 million bucks. The VC and I have spoken about that, and we can do this. The other thing is, and this is the scary part, is I'm on a 5-year contract, the way I see it, okay, is that at the end of 5 years, I might be out of here. It depends on the funding, whether I've been a good boy, etc. We've built this machine up. We need to have the money to take it into the next cycle. So already in 2020, I'm going to start, I've got already plans moving. I need to pull in probably 100 million rand to keep this machine going for the next cycle. Whether I'm doing the next cycle or not, it doesn't matter. Someone else can take over, but the machine is built. But I've got to find that money, because the person who goes in won't understand the nuts and bolts of that machine yet. And then the most important thing that this machine has to do is it needs to do what I was telling you about the ocean governance side. We need to get all this information into ocean governance. So I've kept you here for a long time. I tried to slim down the slides, but I had a lot to say. I hope I've kept you mostly with me throughout the story, and I've tried to do a blend of stuff that people find interesting, but also drop in some science, because Eckhart said, I've got to drop vorticity and baroclinic and barotropic instabilities and stuff like that, because that turns him on. But I know my wife, for instance, she doesn't know anything about oceanography, and she still thinks I take pictures of the ocean. So in summary, I had a slide that just listed all kinds of things, and I just ripped it out. I want to go back to the title. Big thinking, big science. I hope I have done the job of showing you what big science is. Okay? I then want to come back to the question, the provocative question of, can Africa grow the intelligence and the research capacity to fix its developmental problems? And I would like, I hope you can see we can. We can. It's not doom and gloom. We've just got to be smart, and it's about partnerships. And then finally, I want to come, and by the way, equal partnerships. It's not a colonialistic system where the guys come in, and that's what I've got to be so careful when I'm in Tanzania and Zanzibar and these places, is that the UK can come in very heavy-handed at times. And we will do this, and we will put the gliders there, and I'm constantly, it's my job, is say, guys, back off. Listen to what they want, and we will assist them, and that's that equal partnership. And then finally, I want to come to the last little bit of that title that I gave, unconventional title, is Ocean Science and Marine Food Security at NMU as a test case. Can you see why I put it there? Because I actually don't know how the story's going to end. I think it'll end very, very well. And I'm hoping is that NMU and Rhodes and some of the universities who will partner with us can actually start bumping up into those 1,000 universities. So I think that's a good note to maybe finish my talk. Apologies for so long. Derek, I tried to make my speech as long as sometimes yours are. And it was, I should also mention that Derek, as you know, is retiring at the end of the year, and he's very busy, and apparently you asked, could you come to this talk? It was your last inaugural talk, and I hope that I did justice, and I gave a talk that enlightened you about what the vision is and what we're going to do. Thank you.